momentum, I get P1 plus rho 1 Q1. Obviously, I'm looking, if I'm doing a control volume, I'm doing it across the shock itself, so I'm getting really, really close right here, so I don't have to worry about friction, if one wants to think about friction. And I don't have any heat addition, so I'm good. So P1 plus my momentum flow is equal to P2 plus my momentum flow, rho 2 U2 squared. Energy, same principle. H2 plus U2 squared over 2 is equal to H1 plus U1 squared over 2. Now, what important information did I get out of the energy equation?
Stagnation enthalpy. The stagnation enthalpy is constant.
No, velocity. Well, ignore the potential, but what do I get? Yes.
The stagnation enthalpy is constant.
Right on.
2 times.
So, like my fan flow, which is very critical because then what I get at the beginning is stagnation temperature is actually constant across the shop. That is very important information because sometimes I don't know what happens across the shop, and I might not have equations to represent the properties downstream, but knowing the stagnation temperature is constant, I can figure out things downstream. Now, what else do I know? Using ideal gas law, I already know ideal gas law, P is equal to rho RT, and I already know my Mach numbers are still valid, U over A, and I already know my speed of sound is equal to gamma RT. Now, if you take all of these equations, substitute them in there, do the integration over a distance, you are going to get the following equation. Now, we're not going to do the derivation because it's extremely long. Like I said, it's a 5-page derivation. However, I'm just going to write the equations that we need to use for the normal shock. Now, one of the critical ones is the Mach number. So right now, when you go in a normal shock table, you say, okay, what is my Mach number at station 1? Look up my Mach number at station 2. So I'm going to give you the equation that actually drives this. And it's Mach number 2 is equal to 1 plus gamma minus 1 over 2 m1 squared over gamma m1 squared minus gamma minus 1 over 2. And that is one of the critical equations that you generally would use. And m1 is actually greater than 1, and m2 is going to be less than 1.
Yep.
Does that make sense?
Yeah.
Can it be greater than 1?
No.
No, right? It's a normal shock. Everything downstream of a normal shock is subsonic flow. And everything upstream of the normal shock has to be supersonic flow. Otherwise, I would not get a shock. So, and it's a non-equilibrium process, actually. So, but point is, this is the equation that you generally would use in the table. You will take M1, go in the table, and figure out what is your downstream Mach number M2. This equation is the one that goes directly for it. So you sub in the Mach number, and that's what you get for M2. Other properties. Rho 2 over rho 1 is equal to, based on my conservation of mass, is equal to U1 over U2, and that is equal to gamma plus 1 M1 squared. Actually, that's how we drive the equations, is essentially through the density. We use the density to figure out the property change across the shock, and from there, everything else is derived once we know the density function. And this is the function that we end up getting as an integration relative to my inlet Mach number. Now, another one is pressure. Once I know my density, I can figure out my pressure. Because I already have my stagnation temperatures is constant, and I know my static temperatures, then I could get my, and my speed of sound, then I could get my pressure distribution, and that's equal to 1 plus 2 gamma over gamma plus 1 m1 squared minus 1. That's another equation we're going to use, which gives me my property downstream. Temperatures, T2 over T1 is equal to my enthalpy difference, or my enthalpy ratio, and that is equal to 1 plus 2 gamma over gamma plus 1 multiplied by m1 squared minus 1 multiplied by 2 plus gamma minus 1 m1 squared over gamma plus 1 m1 squared. And for stagnation pressure, which is the last property that I'm going to need, P2 over PO1 is equal to a very long equation, and it's gamma plus 1 over 2 m1 squared, the whole thing divided by gamma plus gamma minus 1 over 2 m1 squared, the whole thing to the power of gamma, gamma minus 1 over 2 gamma over gamma plus 1 m1 squared minus gamma minus 1 gamma plus 1, the whole thing to the power of 1 gamma minus 1. So based on these equations, I could get my downstream Mach number. I could get my properties downstream, meaning density if I wanted to, pressure, static temperature. And from those, if I already know my stagnation temperature is constant, so I could also get my stagnation pressure as well, based on this. Or actually, if I already know my static pressure downstream, and I know my Mach number downstream, I can use isotropic relations as well to get it. So generally, you might not need this if you know if you're going to use this. Mostly you're using this. Well, this is a rehash of both together. So it's a complicated long equation, but generally I don't use this. I end up just getting my static pressure downstream, and from there, most likely I know my Mach number through my stagnation temperature being constant, or through this. I already have my downstream Mach number. Once I know this, then I can figure out my stagnation pressure. Okay? So let's take all this and apply it to a problem with the fan of flow, with the shock wave. So example, let's see. I have summed up right here with some diameter, 0.0 meters, and I tell you M2 is equal to 1, and the length is equal to some L, and the friction coefficient is equal to 0.005. You could actually start to notice the transfer friction coefficients. And inlet Mach number is equal to 3.0. Stagnation pressure, 1, is equal to 1,000 kilopascals. And stagnation temperature is equal to 500 Kelvin. So the example is a pipe was added that doubles the length. A shock will form inside. Find the shock will be. and stagnation pressure at the exit. So the classical fan of flow problem with the normal shock, most likely you have to have done this for a high-speed air. Either a homework or exam problem of some sort. You must have seen, not exam problem. Iterated method. The shock location. But you must have done this for a homework.
No.
There was no error.
Okay. Okay. Well, we're doing an example problem. Okay, so here primarily is I've got a supersonic flow going through a duct, and all of a sudden I went to the end and stuck another duct that is the same size as this. Okay? So it's already choked at the exit, and I stuck another duct in there. What's going to happen is I'm going to actually get a normal shock inside. Now, the normal shock inside is not going to happen right at that location, right? The flow is going to readjust, and it's going to happen at some location that I don't know. But right now, what do I need to do to move forward to actually get the location of the shock? What is the first thing I need to know? Well, you usually found a line, but the important problem is, say the pipe was added, then double the length, right? Do I know the length? No. So the first thing I need to know is, what is L? How long is this pipe to begin with? And how much am I really adding? So the first thing I need to do is figure out what is L. So what is L? And like you probably mentioned, it's like Spalding, right? All right, so 4 CFL over D is equal to 1 minus gamma 1 squared minus gamma plus 1 over 2 gamma natural log 1 plus 1 gamma minus 1 over 2 1 squared. So that's my exit Mach number, which is 1, right? Minus 1 minus gamma, my inlet Mach number in this case is 3 squared, minus gamma plus 1 over 2 gamma natural log of 3 squared over 1 plus gamma minus 1 over 2, 3 squared. And from this equation, since I know, this is where the equation is actually very nice. When you know the inlet Mach number and you know the exit Mach number, right away finding the length or diameter, it's very, very easy. And you just chuck them in and put it in the calculator. And what you get is L is equal to 2.611 meters.
That's max.
So for about 2.5 meters at a Mach 3, I'm choking my almost almost like standard conditions roughly. And from there, what you're getting is a choke condition for a 2.5 meter duct. So think of it as long. This cable might be longer, but right here, from this edge to this edge, I have a Mach 3 going through this pipe. I am going to choke it at the end. Now, you went in and actually added another tube to it, and what you're going to get is some shock wave inside, normal shock wave inside. So I already know my length. Now, my new length is what? So I can just say, okay, my new problem is essentially, what are my inlet conditions? How are my inlet conditions going to change? Well, this is a supersonic flow. If I double my length, my flow is not going to readjust. All it's going to do is I'm going to get a normal shock, so my inlet conditions remain the same. So meaning that my M1 is equal to 3.0. My stagnation temperature is equal to 500 Kelvin. My stagnation pressure is equal to 1,000 kilopascals. Assuming that it's long enough that I choke the flow in the downstream, and somewhere here, I'm not going to draw it in the center, somewhere here, this is station 1, let's make this station 2, and let's make this station 3. Somewhere here, I get my normal shock, L1. And my total length based on this length is now 5.22. And assuming the same friction coefficient that we had before, now this is my new problem. So, I have my inlet conditions. I don't know where this normal shock is. I need to find out where L1 is, and once I know L1, I can figure out station 2 and station 3. So what do I do? Trial and error. That's one way to do it, but you can't actually confine it because you have the equations to confine it if you assume that this is choked in the end. So one way to do it is to do trial and error right away. Assume your length, solve the problem, and see if that condition actually chokes it for you or not. If it doesn't, you keep going about it. However, if I know my conditions of fan flow from supersonic flow to my station 2, and know my conditions from station 3 to my choke condition, and know a relationship across the shock that can find the whole problem without trial and error. This I have to do some iterative method, but I have 3 equations and I'll have 3 unknowns. So essentially, so we don't have to run out of time. Let me write the equations so we're going to move on. So let's do a fan flow from here to here first. Well, I already know that for CF, L1 that I don't know, that's unknown, divided by V is equal to 1 minus gamma M2 that I don't know, minus gamma plus 1 over 2 gamma natural log of M2 squared, 1 plus gamma minus 1 over 2 M2 squared, minus my inlet condition, which I already know, 1 minus gamma to the power of 3 squared minus gamma plus 1 over 2 gamma natural log. Obviously, we're assuming gamma here for all the problems so far. Since no propulsion system is air, so it's 1.4. Natural log of m1 squared, which is 3 squared, over 1 plus gamma minus 1 over 2 m, which is 3 squared, sorry. 3 squared. And that will be my first equation. I'm trying to find out L1, that's the critical information I'm trying to find out. What I don't know is M2. So I got 1 equation and 2 unknowns. I could use my fan flow from 3 to the exit condition, which is 4. So if I assume this is station 4, M4, station 4. So I could use fan flow for that and say, well, for CF, now I could take the this distance right here as the subtraction of 5.22 minus L1. So say this distance from 3 to 4 is simply 5.22 minus L1. Now you're seeing what I'm doing here is trying to keep everything unified in terms of my parameters I'm trying to figure out, which is L1. Divided by D is equal to the same equation as the top, except I don't know everything at 3, I know everything at 4, so I can say minus 1 over gamma multiplied by 1 minus gamma plus 1 over 2 gamma natural log of 1, if you want to, 1 plus gamma minus 1 over 2, 1 square minus the whole thing, minus 1 over gamma m3 minus gamma plus 1 over 2 gamma natural log of m3 squared over 1 plus gamma minus 1 over 2 m3 squared. And that is my equation 2. Now, what do I don't know? I still don't know L1. And I know this. What do I end up with? This is another unknown. So now I have L1, I have M2 that I don't know, and I have M3. So I have 3 unknowns and 2 equations. What do I do? What else is there? Shock equation. So I already have a relationship between M2 and M1, which is my normal shock relationship. M3 squared is equal to 1 plus gamma minus 1 over 2 M2 squared over gamma M1 squared minus gamma minus 1 over 2. So using that relationship, I already have 3 equations, which is, this is already known, this is not known, this is not known. So using the 3 equations and 3 unknowns, this is my equation 3, I could solve for the Mach numbers, and let me just write the solution here before I run out of time. L1 is equal to 0.4816, M2 is equal to 2.472, and M3 ends up being 0.51. All I have to do is just solve simultaneously for the 3 unknowns, 3 variables that I don't know. Once you know those, now I could go and actually get
for the Mach number in the second
whatever I need, you know, P stagnation 2 or P stagnation 1 from fan flow, and, and P stagnation 4 over P stagnation 3, again, fan flow, and if I want anything across the shock, P stagnation 3 over P stagnation 2, normal shock. So the equations become straightforward there.
Okay, we have a question in the back.
For the first equation, the first,
That's weird, yeah.
would be squared?
You tell me, let me just check the equation.
I don't think it is.
I get the one on the bottom. I get why it goes in Mach 1 because it goes from Mach 1 to M3.
It's not.
But it should be
Yes, you're correct.
Mach. It should be Mach at the inlet, which is 3.
But he's saying that we don't know in Mach 2, so
No, that's what I'm saying. You're gonna find it. What I'm saying is that one should be over there minus at the Mach 2 one, and then this one over here is right because it's M1. Mach equals 1, and then it goes to M3, which Mach is less than 1. It should go.
Shouldn't that be over gamma and 2 squared minus?
That one should have been first,
no,
minus
I just get confused with
the
that.
M2 one.
All I know is
Yeah, you're right, you're right.
M2, you see? M2, he is M2.
Yeah, it is. Kyle.
I have a question. Do you add this to Dropbox by chance or anything?
I have it on